Hello. Physics doesn't only help us explain what happens inside the lab, it can also help us explain what goes on outside. And today we've brought some fairly unusual things into the physics lab. We're going to try and find out how they work. So we brought loads of musical instruments in, and we're going to try and use our knowledge of sound and what we've learned about the physics of sound to understand about the musical instruments. But first of all, we're going to have to do a little bit of revision on the theory of sound using the guitar and the tin whistle to try to remember what we know about the theory of sound waves. So first of all, here's Richard to talk about the guitar.
Right, hello. Here we have a 6-string guitar. It's called a steel strum guitar because the strings are made of steel. When I actually play a chord, the strings start to vibrate. They vibrate between 2 points, the nut and the bridge. Each string is under tension or pull. I can alter this tension by adjusting this key. As I tighten the key, there's more pull on the string, the note gets higher or the pitch gets higher. I slacken the string and the note goes down, or the pitch decreases, gets lower. Also, each string is of a different thickness. Heavy strings give low notes, lighter strings give higher notes. Also, there is also one other way of altering the sound, or the pitch, and that's by altering the length. Here I'm actually decreasing the length. I'm shortening the string. Here I'm lengthening the string. The note goes down. You probably recognise this as a 6-stringed sonometer, where you've got your sound box here. Now if we can just have a look at the guitar up here. I think we've got it here. We've got sound box here, nut and bridge and the wire under tension or under pull. When I actually pluck a string, what happens, you get like a C wave which travels up the string, hits the nut where it's fixed, rebounds back, and that which is called a reflected wave, and the vibrations go up and down to form a standing wave. Let's have a look at our first standing wave. Here we are. We have the black line is the wave travelling up the string, hits the nut and is reflected back, and we get a standing wave. This is the simplest way the string can vibrate. It's fixed here and here, we call those nodes, and where there's maximum movement we call that an antinode. We call this the fundamental. Now, what I'm actually going to do now, I'm going to hit the string and place my finger halfway along the string. I'm not actually going to shorten the length of the string, I'm just going to place my finger lightly on. In other words, I'm going to make a node. See if you can actually hear. Do you maybe notice a very high pitch note? I'll try it on this string. Let's have a look and see what that looks like. You can see here we have a node where I place my finger, and that makes the wave or the string vibrate in that particular way. We call this the second harmonic. I can also place my finger a third of the way up the string. Try it on this string. This one. Let's see what that looks like. Does it look like that? Right. This is where I place my finger. It makes the string vibrate in that fashion. We call that the third harmonic. Node, node, node and node. Antinodes here. Now, these standing waves are not actually the waves we hear with our own ears. As the string vibrates between the nut and the bridge, the vibration passes through the bridge into the sound box, causes the sound box to vibrate, which causes the air inside to vibrate, and it's the vibration of the air molecules that we actually hear. I think we've got a little diagram here explaining this. Yeah, here we are. Here's the sound box of the guitar. The wave comes out. We've got areas of high pressure where the air has been squashed by the sound box, and areas where it's been thinned out. We call these, where it's been squashed, compressions, and these rarefactions. We call this a longitudinal wave. And it is these waves that we hear with our ears. Yeah, that's it.
Now, Richard has already shown us how the guitar makes the musical noise. I'm now going to try and explain how the whistle makes the noise. We saw with the guitar that it was standing waves in strings transferring the vibration to the main body of the guitar that made the noise. With the whistle, it is the standing wave inside the pipe transferring the vibration to this top part of the whistle here. I don't know if you can pick that up, called the fipple of the whistle, which makes the noise. When I blow, it's the fipple that vibrates. Now if we can have a look at this overhead projection, you can see a rather large whistle and a small little girl. It's this part of the whistle vibrating very quickly, causing the compressions and rarefactions of the air, which we hear as sound. Now to get the fundamental on the whistle, fundamental note on the whistle, all I do is blow fairly softly with all my fingers on the holes like this. That's the fundamental note on the whistle. We'll have a look to see what this looks like on the transparency. There's our whistle. I'll just explain. Right, now Barbara can just hold the corner of this down, please, Barbara. Thank you. Here we can see that the air inside the whistle is vibrating most at the ends, the open ends, here at the fipple and here at the end, and isn't vibrating at all in the middle, here, at the antinode. Now, if I play the whistle again, that's the fundamental. If I blow harder, I get the second harmonic. If you can see what this is like, please. Looking very good today, Barbara. Right, and on here we can see we've got nodes here and antinodes here. So the air is moving a lot here and not much there. Now again, I can blow harder still and get the third harmonic. Here's the fundamental note. Here's the second harmonic. And here's the third harmonic. I'm not changing my fingers, shortening anything, I'm just blowing harder. So if Barbara could show us the third harmonic. Thank you, Barbara. 5 o'clock, all right? Here's the third harmonic, again with antinodes at both the ends and nodes here. We always have antinodes at the end. That's the important thing. And again, I can blow still harder and get the fourth harmonic. That's the fourth harmonic. Now, if I just used harmonics, I wouldn't get much of a tune out of a whistle, just going. You can only get so many notes. How do we get the other notes? Well, what we do is we shorten the effective length of the tune by lifting our fingers up here. Just as we did with the guitar string, by shortening it, the note went up. It's the same with the air column. Here we have, thank you. Here we have a whistle with the air column shortened. You see, we've lifted one of the fingers up here, and we have a shorter fundamental. So we have a shorter fundamental like this, and I can still get the other notes, the harmonics. I can still get them. Now if I just move over here quickly, we'll have another look at a different open pipe. This is a flute. The only difference between this and this is that this costs about £170 and this costs £1. Other than that, we blow across here So it's this part here which vibrates to make the standing waves in the flute to make the sound. We'll be explaining in a bit why the flute sounds different from the whistle. Now if Barbara puts up the transparency again, here we have the flute vibrating between here and the end of the flute. Now I'm just going to talk for a minute about the head of the flute. Here's the head. That's the fundamental for the head, as we could see. Now if I put my hand over it, over one end, like that, I get a closed pipe. And listen to the difference in note as I put my hand over the end. And that is only because I'm putting my hand over the end. I'm not changing my breath at all. So let's have a look at that, see what happens. When we have a closed end, like this, we can't have any vibration of the air in there. So we have to have a node here. We still have a node at the open end, we have to have a node. And this makes the wavelength twice as long, but we won't talk about that for the moment. It makes the wavelength twice as long. So open and closed pipes make their noise sound by standing waves inside the pipe, causing vibrations, compressions and rarefactions in the air. Right. This is a flamenco guitar, and you'll hear in a minute that it sounds different from the steel strung guitar that Richard played. First of all, it's got a much more mellow tone. Now when this was invented in Spain to be used in the dancing there, so they obviously couldn't just play it like this because it's not loud enough. So they developed a method of playing to make it louder. Like that. But why does the flamenco guitar sound so different from the steel strung guitar? Richard will tell you why.
Right. We've already told you that when you actually pluck a string, it actually vibrates in many different ways. It can vibrate in the fundamental, the simplest way, the second harmonic, and the third harmonic. Each string vibrates in all these ways at the same time. What we're going to consider now is just the fundamental, which we have here, node, node, antinode, and the second harmonic, here with a node in the middle. Now, if we actually add these two waves together, like on graph paper, we actually get a peculiar wave shape. We actually get something like this blue line. This is actually the resultant of the two waves added together, the fundamental and the second harmonic. When we actually hit the string, we actually produce, as we found, compressions and rarefactions. Right at the very beginning, we get a very quick compression and then a very, very slow rarefaction. And it's this mixture of harmonics and fundamentals that give the actual instrument its tone or its quality. We'll now consider just looking at the fundamental and the third harmonic. Here we've still got the fundamental, the node at either end, the node in the middle, well, antinode in the middle, sorry. And here we have the third harmonic. When we actually add the two together, we get, when we add these two waves together, remember, node there, node here, we get something like that. You've got to admit that is a very different wave shape from the one before, and it will sound differently to your ear, because we have compression, rarefaction, and then another compression. We call these harmonics that are mixed in with the fundamental, overtones. Certain instruments are richer in certain harmonics than others. So it's these presence of these different harmonics that actually give the actual instrument its tonal quality, and that's what makes each instrument different. That's it.
Now, this is a mandolin, and it works in the same way as the guitar works. The strings vibrate between here and here, causing standing waves in the strings, which make the body of the instrument vibrate to give the sound waves, the pressures and rarefactions that we hear as sound. Now, guess where this instrument originated from? Yep, Scotland. This originated in Italy, but is now used a lot in Irish music, and it's got a very metallic sound because of the harmonics that it has in its makeup of its notes. So that has a metallic tone. Now the father of the mandolin is this chap. This is a bouzouki, which is a long-necked lute which originated in Arabia, and is now, then it went over to Greece. And again, this is often used in Irish folk music again. This again has a metallic sound. That's the sound of a bouzouki, another metallic sound, but the way the sound is generated is exactly the same as with the mandolin. Something a bit different now is the banjo, which was invented by the slaves when they came over to America, and again now is used a lot in Irish folk music. It was a sad fact that slaves could very rarely play the banjo properly. This doesn't use a sound box like the mandolin or the bouzouki, but has a drum head very tightly stretched. And we'll be talking about the banjo just a bit more later. Now, all stringed instruments sound roughly the same because the mixture of harmonics that they have is roughly the same. A group of instruments that sound very different is the woodwind instruments and the reed instruments. And just behind me here, I have a harmonica. Now, harmonicas were invented in Germany, very near where Beethoven was born, and nowadays they're used mostly in blues music. This is actually a blues harmonica, and what makes the vibrations here is reeds inside the harmonica. Right, this sounds a bit like this. Etc. So you can play and look like a dirty old tramp. The last instrument we're going to see is the most difficult one to play and the most complicated, and it is the bagpipe. Just like the whistle and the flute, it has a fingering pipe which you play the melody on, but in addition to that it has what are called drones, which provide a note. If we just have a close look at the chanter, you can see that it's got the holes in to make the effective length of the tube shorter, just like with the whistle. But instead of having a whistle head or a flute head, it has this, which is a reed, which sounds by itself like this. Like that, just like a piece of grass between your thumbs. And it's the reed vibrating which makes the sound. We put it in the pipe. That's the sound of the chanter by itself. So I'll put that back in here and get wired up. What I'm doing now is pumping air from the bellows into the bag. Like that. That's the drones getting warmed up. I don't know if you've heard a cow in labour, but it sounds very similar to this. Now that's the sound of the Northumbrian pipes. So what we've discovered is that all instruments sound differently because of the different recipe, the different amounts of different harmonics they have in each note structure, providing that different shape of standing wave. And we've also found out that reed instruments use reeds to vibrate, stringed instruments use stringed, and the whistle and the flute uses the vibrations of that edge of metal or plastic. Now there's one more instrument which we're going to see which doesn't appear to have anything vibrating in it, which Richard's going to show you now.
As you can see, we have a guitar which still has strings, but we don't seem to be getting that loud tone, we don't seem to be getting a loud noise. We're still getting strings that are vibrating, the vibrations are passing through the bridge to this guitar, but there's no air inside. And remember, it's vibrating air that we hear. So can you think what is actually vibrating to cause the sound? Because remember, something does have to vibrate. Here's a bit of a clue.
Don't put one in there.